we're gonna look at a new concept today, which is something about expanded hierarchy. But before going there, I just want to recap again about expanded decomposition, right? So this is what we have. Given any graph G, a node weighting A, and parameter phi, we can cut phi, something like phi log n times A edges, so that A is cut expanding. Okay, so that's expanded decomposition. We have seen this. By the way, I'm gonna call this log n thing the overhead factor. Okay. All right. Good. So, and we see how to construct this too, which is just as long as A is not expanding yet, it means there must exist a sparse cut. So cut that and repeat. However, this is easy to understand and nice. The only issue is that to check if A is expanding or not, that is NP-hard problem. So it's not too clear how, like, this is like not a fast algorithm, okay? But I want to claim that just by changing it by 1 bit in this algorithm, we already know how to do it, how to make it polynomial time already. And here is the algorithm. So we just basically check if A is flow expanding or not. Okay. And here by here I mean like check if the the A product demand is routable with low congestion or not. Okay. But that is something that you have seen before, that to check if the product demand is routable or checking if some demand is routable with low congestion. This can be modeled as a linear program. So this is something that a linear program you can solve it in poly time. So this is something that you can check in poly time. Yeah.
Does the e wind up being in like an exponent or something? Like I'm trying to figure out why you can do this in polynomial time, but not in the expansion version.
Oh, so it's just that, well, to check if it's flow expanding, like we see the linear program that capture the problem.
Right.
But there is just no linear program that capture cut expansion.
Okay.
Yeah.
Does it turn into like a mix or like an integer programming thing if we're trying to do cut expand?
Say again.
Does it turn into like integer programming if we're trying to formulate it as like cut?
It's going to be integer program, not linear program. Yeah. Okay. So my point is, anyway, you can check this in poly time. Okay. So just try to convince this. Just like maybe I said this instead. Check if the A product demand, just fix some demand. Yeah. Let's say that A product demand is routable. It's not routable. Yeah. It's not routable with congestion at most 1/5 in G minus C. Which is just to check, like if this demand is routable or not. This you agree, right? We have seen linear program that capture this. Yeah. You check this. If it is routable, then it means that A, but if so, then A is basically what? Phi over 2 flow expanding. And we can just say we are done. expanding. But if not, okay, then it's not flow expanding. But we also seen that if it's not flow expanding, we can actually find a cut that is sparse. But here we can find a cut that is sparse, but how sparse? It's just phi log n. We have seen this in the proof. Like from the proof to bar a flow cut gap, that proof is completely algorithmic. We first solve the LP and then run low diameter decomposition from the LP and do some sweep cut. That's it, right? So that proof gives you some sparse cut, phi log n sparse cut, and that is polynomial time. Okay, so the algorithm then is just check if it's flow expanding. If not, find some sparse cut, like some phi log n sparse cut, and then cut it, and then keep doing this until you're done, until like A become flow expanding. So after terminating, we see that A must be phi over 2 flow expanding, which means it's also phi over 2 cut expanding. And then we just need to bound the size of C. Okay. What would be your guess? What's the size of C? So we had before that C, like in our previous proof, C would have size something like phi log n times A. Now this is like a phi. Like instead of phi here, we have phi log n here. What do you think? Like, what's the best bar we can get on the bar of C? Yeah.
Would it be like phi log n together squared, or?
Yeah. Phi log n together square.
Yeah.
You can get better than that. Actually, this is not quite right because. Yeah, actually, why do you think so? Yeah.
Well, it's, when we were doing with the cut expansion, I mean, when we were looking, not flow expansion, but cut expansion, like we were looking for a phi sparse cut. So that's kind of what I thought. Instead of phi, what if we look for a phi log n sparse cut? And then.
Yeah, like you have a correct reasoning, but it's just that I don't see why there should be square on the phi. Okay. Kay, do you want to say something?
Yeah.
What do you think it should be?
We should just be incurring an extra log n factor on the size. And this also kind of ties into our knowledge of like flow cut cap as well.
Yeah. So the idea is that the correct bar is just you pay another log n here. Like basically you replace phi here with phi log n. So it becomes phi log n square. So the idea is just, you can just look at the same proof. Everything that I highlight here used to be phi. And now it's just phi log n. And so like, everything used to be phi, now it's become phi log n. So this is like a phi log square n times A. Okay, that's it. So you can verify this yourself. So what we get is that, okay, given the graph, the excess poly time algor that find phi C, and the size of C is this. Okay. And this implies that A is also phi cut expanding 2 in G minus C. Question about this? So we just see now that like just by paying another log factor in the overhead, we can make it poly time. Good. Okay, let me question. Okay, now let me mention the state of the art. So the state of the art for the overhead in the expanded decomposition. So This thing, the log n here, you have seen it. Okay? For flow expansion, log square was actually the best known. Basically, you just saw this. Basically, you pay another log n from the flow cut gap, but the proof for the flow cut gap is algorithmic. So this is polytime. This is just actually existential proof or exponential time. And previously, there were like some algorithm that try to make it faster. Like you can pay a bit more the log n and make it faster. And what you will learn like later in some weeks is that we will see how to get algorithm that takes just nonlinear time, something like nonlinear in number of edges over phi. So if phi is not too small, then this is nonlinear time. Yeah. And this is log cube. Okay. This is like some algorithm that I showed some years ago. But yeah, this is something that I mentioned last class, last Thursday, that now we know how to get this. It's just close to log n, but it's like log n times exponential of square root log n. So this is something that this is like less than log to the 1.1 n, but yeah. So, and the techniques that we learn is useful for this one, but I will not have time to talk about it. Okay, that's the state of the art, so that you know. Okay, so now today new concept. Okay, we will learn this thing, separator-expanding hierarchy, which is some type of expanded hierarchy. It's a really powerful one, and we will learn this through by trying to solve some problem. That problem is connectivity oracle under edge faults. Okay, I tell you what this is, and we will first show how to solve this problem on expander. Like usual, like you just start solving problem on expanders, and then we generalize it to general graph using the hierarchy, which you learn what it is. Okay. So what is this problem? Connectivity oracle under edge faults is a data structure problem where you start with a graph, okay, still undirected graph, let's say unweighted, yeah, just some graph. Okay. You pre-process it. Let's say you can take any polynomial time or anything. You don't care, just pre-process a graph and build some good data structure on this graph. So that next, there will be an update D. So think of D here as not as a demand, think of D as a set of deleted edge. D is a edge set, right? That has D edges. Okay. And we want to spend, given this failure, given these faults, we want to spend some time like D, spend D time on this phase. So that the last phase, given S and T, which is, what is this? I can check if S and T are still connected in the graph after deleting D. Okay. Now I want it to be really fast, maybe log n time, something like that. Okay. So O tilde, again, I just hide some log n factor. Okay, does it make sense? This is the problem. Yeah.
Is D given originally in the problem, or like some initial set D? Or?
No, D is given at this point. Like this point, you don't know what D is, and this point you just know D. You don't know S and T, and this point now you know ST.
In the first phase, we don't alter the graph in any way. We just do some computation.
Yeah. So.
Can we add edges?
You can see that you can add edges soon, but exercise after you see this, yeah.
So if we like deleted all the edges into the connected SMT, it would return false, right? This is you can change the state of SMT.
Right. So for example, in the beginning, the graph looks like this. This is S, this is T. If I delete just one edge here, then this query would just return yes. But if I delete these 3 edges here, then at the query stage, you would return no. So it's kind of natural problem where like you think like you have a map and then some earthquake happen, the road get broken, and you still want to know if S can still reach T. Yeah. You can talk about distance too. Like instead of connectivity, you can talk about shortest path. Okay. And indeed, the techniques here can generalize to shortest path, but you learn about just connectivity. Okay. All right. So that's our goal. And here's the algorithm. Let's try to look at this problem when the graph in the beginning is an expander. Okay. And also, I assume more. I assume that the target, like S and T, is fixed from the beginning. I just focus on 2 vertices, like one city, like Ann Arbor and Detroit. Yeah, just fix that. Yeah. Okay. Yeah, for some reason we want to go to Detroit. Yeah. So, okay. So before I describe the algorithm, let's start with some intuition about expanders. Okay, this is expanders are robust, but I wanted to make it clear to you in what sense it's robust. Okay. Let's say that G is a phi expander, and then let's say that I delete some edge set from G, okay, and let U be a new connected component, like you delete something from the graph, so some part kind of got split from the graph. So let that be U. Okay. So U is not like a giant one, the large part, like it's something that's split out of the graph. Okay. So the claim is that the size of U. So when I say volume, what has volume here, I just really mean the degree of U. Okay? So U has volume or degree U is just going to be at most D over phi. That's the claim. Meaning that if I delete, let's say 10 edges, then the size, the volume of D should be something like 10 over phi. Yeah.
What's the lowercase d in this case?
Oh, D, the lowercase d is the size of D. Yeah. Yeah. Okay. So meaning that this can happen. This kind of scenario cannot happen. That is, if I delete just 2 edges, then it split the graph into 2 balanced parts. That is like now U is really big. I want to say that this kind of thing cannot happen. And it makes total sense that this cannot happen, right? Because if this can happen, then there is a really sparse cut. So, okay. So let's try to prove this fact formally. Any question about this statement? Okay. So now, let's say this is a graph, and the red edges is the edge that I remove, that I delete. The red edges is D, is the set D. I delete it here, 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 here. So let's say that after deleting, like the graph split into parts. There are maybe this part, this part, this part, and then there is some giant component here. Yeah. So by giant component, I just mean the one that has size, the volume more than half. This is like more than half. Volume is more than half of G. Okay. So let's look at some component U. Maybe let's look at this guy. Okay. And then the point is that all the boundary of U here, they are all deleted, right? So the boundary of U have size at most D, D, which is just D here. Yeah. The boundary of U is just of size D. D. But at the same time, we know that the graph is an expander. So it means that this is at least phi min degree U and degree V minus U. But this is a smaller side, so this is at least phi degree U. Okay. Now combining these inequalities, you get that the volume of U is at most D over phi. All right. So this is what I mean by the robustness of expander. If you delete small set, it can split off only small set. That's it. Okay. So, okay. Like the connectivity of, like the expander is not just some connected graph, it's robustly connected. Yeah. Okay. Okay, so this is just something you keep in mind, deleting D thing, disconnect D volume. Yeah.
But this also works for like if we split out multiple connected components, right?
Yeah.
Like if there are many
you can say that
components,
all the components that split off,
summation.
the sum is at most D. Yeah, the total volume of split off component is at most D. Okay. Okay, so with this in mind, then let's see the algorithm, the oracle on expander when you fix S&T. Here's an algorithm. Okay. So fix, I know S, because S and T is fixed, are fixed. I'm just gonna, let's say S is maybe here, okay? What I'm gonna do is, I'm just gonna do DFS in the graph after deleting D. And let's say I'm gonna explore this mini volume, meaning that, let's say if S is here, I just do DFS, and then like, you can think of volume here as like the number of edges that you have visited so far, okay? This is, maybe just think of this as number of edges visited so far. So just do DFS. As long as you didn't visit 2D over 5 edges, then you continue. Okay. And two things can happen. Either you got stuck before this threshold. If you got stuck, maybe like you are here and you explore everything and you cannot go further. Then basically you get, you identify the isolated component. Call that as US. That's the component US. Otherwise, you're not done exploring. Maybe you are here and you explore. And you explore, but like, you still can continue. Then you just claim, I just claim that like now it means that S must be in the big component. Okay. Does that make sense? I mean, this is true, right? Because the pink component, the volume in total is something like d over phi. So if I start inside here, I would identify the component that contains it. Yeah.
I guess I'm just wondering if you're like maintaining this data structure for a long enough time, after a certain number of updates, couldn't G become no longer an expander? Like if you just, I don't know, there's like some large cut, but you delete everything from that cut.
I understand. So we are consider like that makes sense if you have many sequence, like a long sequence of edge deletion. Here we really look at one batch updates.
Okay.
Like you are given D, and I just want to see if S and T is still connected after deleting the set D. There's just one single batch of update. Yeah.
We're exploring like 2D over phi volume. Is it because just to make sure if we're in the big component, because it's like bigger than half, or?
Yeah. Like, I mean, not to like it's more like if you start from the small component, you know that this component has volume less than 2D over phi.
Yeah.
So if you start from the small component, you know that you will like got stuck inside the component for sure.
Mm-hmm.
Yeah. And you just say that, okay, the component that you got stuck, that's the component of you. Yeah. And if you are not inside the small component, if you can still continue, you know that you are not in the small component.
So you must be in the big.
Yeah. Okay. So you see that you can just identify which component S is in just by spending something like order of D over phi time. And now do the same for T. Spend another D over phi time. And just return yes if the components are the same. That's it. So the correctness is hopefully clear. And update time is just T over phi. Do this from two vertices. Okay. So that's like a warm-up. So now let's see how to solve this problem when you don't fix S and T. Okay. It's going to be a bit more complicated. Yeah.
Previous algorithm, can you just see if you saw T when you explore from S? Like instead of like checking if the components are the same.
Yeah. If from here, if you visit T, then you know for sure that S and T are in the same component. Yeah.
Oh.
Yeah. Or moreover, like if you are in this case, if you identify the component of S and you didn't visit T, then you also know that T is not in the same component. Okay. So I'm just doing something a bit stronger. Yeah. Okay. So here, let's look at our original goal, where we don't actually know which S and T we will query. Okay. And what I'm going to do is something a bit stronger. Instead of preparing, like doing something here, I just said that after phase 2, let's say we just try to get the representation of connected components, of all connected components of G minus D. Okay. And this representation should be such that now given any ST, now you can query this fast. Yeah. I'm just rephrasing the goal. Okay. We want to, after phase 2, we now kind of know all the connected components so that you can query anything fast. Okay. And here's the algorithm. So this is just some picture, right? And again, imagine that the red edges are my deleted set D. Okay. And like, so we don't really know, like, this is how the graphs look like after deleting D. But we don't know this picture. We don't see it. We kind of want to identify the connected component. Yeah. And what we're gonna do is this. I'm gonna start my data structure by initialize something that, let's say I call it region for each node. So for each node V, we just set that the region of V is a singleton node. Like region of this node is V is a single node here. A region of V, this node is just here. So you just start with singleton region for every node. Okay. And initially they are all passive, but some region I will declare to be active if the following is true. If the degree of the region is small compared to deleted of U of the region. What is this? This is just kind of the degree of U with respect to deleted edge. So just count the number, count the number of deleted edge incident to the region. Okay. So if the region is kind of relatively contains incident to many deleted guys, then you call it active because it's kind of dangerous. Like you kind of want, if you kind of want to check if it's disconnected from something or not. Yeah.
Can I clarify? By degree of U, you mean like the total number of edges within U, not like just the edges going out of U to the rest of the graph?
No, it's the sum of degree of every node in U. So it count both, right? Yeah.
Okay, yes.
Yeah. And more to the small point is that the edge inside, you would count it twice.
Okay.
But
okay.
it doesn't really matter. Yeah. Okay. The same is here. Like you count both, both inside and the one that cross the set. Okay. Okay. Also, I'm gonna say that I need another condition which say that this region still have some unexplored neighbor. So in our algorithm, we will do some DFS kind of like before. We will keep exploring, but if we explore and now we got stuck, then we should claim that we are done with it and it's not active anymore. So only the region that we and we are not done exploring yet, we claim that it's active. Make sense? This is just definition. Okay, let's see the algorithm. The algorithm is that as long as there is an active region, the region that looks like dangerous, whether it's disconnected or not, we do something. We're just gonna say that, suppose that U is active. So there must be some unexplored neighbor of U. Let's say that this is like my region, okay? And I didn't explore some edge incident to U. So maybe this is just in general, let's say this is my region U. Okay. The neighbor here would be like the edge, like the neighbor that is not in U and there is an edge from U to it. Okay. So what we're gonna do is just let V be the unexplored neighbor of U, like this guy. And then I'm just gonna merge the region between of U and region of UV. Then this region will be merged like this. And then we just check we check if now in the new region, like the degree is big compared to the deleted edge incident to you. If it's now big compared to deleted edge, now it's kind of safe. You say that it's passive again. Okay. But on the other hand, if after merging, then there is no unexplored neighbor left. Like for example, if my region is just exactly this thing, U, and I cannot, there is no other edge in G minus D that I can go further. There's no other neighbor. Then I just say that it's now passive. It's now isolated. We are kind of done with it. We identify the component.
When you say degree, do you mean degree in G or G minus D?
Degree in G. Yeah, good point. Yeah, but degree in G. Okay. So that's the algorithm. So at the end, like when I keep doing this, you know that at the end you're gonna have only passive region or isolated region. There's no active thing left, just passive or isolated. For the isolated one, you know that this is like just one connected component after the deletion. You have identified the whole thing. You cannot go further. So you're gonna get a bunch of isolated guy, each of which you know that it's just one single connected component, and a bunch of passive region. The claim is that the components of G minus D really is just a bunch of isolated region. Each of them is isolated one. And the union of passive region is just a giant one. Everything like passive region are actually in the same component. That's the claim. Okay. So that's algorithm. Let me kind of I spent so much time to make this animation, so let's see. Actually, okay. Like in the beginning, a lot of guys here are passive, right? But you know for sure that the node which is like the endpoint of deleted edge is gonna be active. Each of these guys is actually active region, right? And okay, let's say that we start exploring from this active region, and then we're gonna merge thing, and this now become isolated. The purple thing is isolated. And then just look for the next active guy, maybe each of this guy, and explore a bit. Now this become big enough. So there are just two deleted edge compared to this volume, so it become passive. This guy become passive too. And can do the same thing here. You explore from this guy, this become isolated. And this, you explore from each of this, each of which become passive. So you can see that like sometimes you know that this is actually disconnected, but you might like at some point you might just say that this is passive. But you know that you will not finish actually, because each of this is active as well. So what you're gonna do, like the algorithm will do something like exploring from each active guy, and it will keep kind of merging the active thing. This is active. Like it's like you explore from this guy, and now it merged with this region. So this become active. And you keep exploring from the active one, and now you identify like now it become isolated. Okay. And continue. Okay. So that's it. Like now you're gonna get like you get isolated the purple thing, and a bunch of passive one here. And the claim is that every passive thing is actually the same component. So that's hopefully clear.
I guess it's unclear to me why there can't be like a small isolated component that's just never visited by the algorithm.
Oh, like, because in the beginning, I really just claim, like, initialize the region of everyone to be isolated region.
All right.
Yeah.
So that's like for every V.
This is for every V.
Okay. Okay, gotcha.
Yeah.
That makes sense.
And it makes sense that we will not actually visited many regions, because we the idea is that we continue exploring only from the active guy, and the active guy incidents to many deleted edges. So we gonna explore only something close to the deleted edges. The part that is far from deleted edges, we would not even touch.
So the endpoint of the deleted edges were initially active.
Yeah.
So why was it active?
Oh, because good point. I mean, not everyone, but let's say that your degree, if your degree is less than, let's say like if you are incident to deleted edge, then this thing is at least is 1 at least, right? If your degree is less than 2/5, then you will be active. If your degree actually is more than 2/5, you are still not active. You're still passive. Good, yeah. So you will become active only if you have low degree and you are incident to deleted edge.
Think about that, and it's like, I guess what I want to think is that if we have like a couple of high degree vertices, then deleting like 1 or 2 edges probably doesn't change the
Exactly, yeah. Like the graph is expander. If you are high degree, you know that you connect to so many guys anyway. Even if you delete, the point is like if your degree got deleted less than 5 fraction of your degree, if your edges got deleted less than 5 fraction of your neighbor, then you are still passive, yeah.
So, is it possible for like a component to go from being can like a subgraph go from being like active to then having part of it become isolated, or
Yeah. So
I'm just wondering about runtime here. Do you need to like look at every at the start of each while loop? Do you need to look at every possible view, or?
Oh no, good. Let's talk about this implementation details later. Yeah. But the point is like you will not look at all the region. You will just like you just need to scan, like look at like the region that could become active at all need to be incident to deleted edge. So you just need to scan at region that incident to your deleted edge. So you spend time proportion to D, not the whole graph.
Sure, that makes sense.
Okay, so let's prove this claim. I want to claim, all I need to prove is that all the passive region are in the same component. If we can prove this, we are done. Right? We really get the representation of all connected components. Okay. Let's prove this. All the passive region are in the same component in G minus D. Suppose not. Suppose that, let's say that there is some component B. Let's say B is less than half. If there is a component, it must split into 2 components, one of, like, say that you take the smaller half. Yeah.
What does, suppose not, or suppose
Oh,
that there does not exist?
Suppose that not all regions are in the same component.
Oh, I see.
Means that this region maybe like they split into some parts, some connected component like this. So first of all, you know that okay, so B is a component in G-D because and also we know that the structure of B need to look like union of passive region, as in like B cannot let's say B cannot be like this. That is like it cross the passive region. Why is that? Yeah.
Passive regions created by merging neighbors.
Exactly. The passive region we know that is connected. The reason that it become passive region is because you merge the neighbors. So this part must be connected. So it just cannot be the case that the connected component cross this connected component, right? So it must look like something that respect the region. Okay. So let's say that you have B like this. It must respect the region. So, okay. On one hand, you know that the number of edges crossing B is going to be at least 5 times degree of B. Because this is an expander. There must be a lot of edges crossing B. Okay. But at the same time, okay. But what do we know? We know that the number of deletion incident to B must be small compared to the volume of B. Why? Because each of these are passive region inside B. Each of the passive region is such that if this is U, then deleted of U is less than 5 degree of U, over 2. That's what it means to be passive, right? Like you can just now sum deleted U over all U in B. So you get this, that deleted edge is not too big. Okay. All right. So what does it mean? There are a lot of edges crossing B, but the thing that you can delete is like less than half of what you can cross B. So like you can delete it only like half of this guy. You can delete only half of this guy. There must still be an edge. There must exist an edge that cross B that you didn't delete. But that means that B is not actually a component in G-D. You can still cross B to some other part, right? So there must actually exist some edge crossing B that is not deleted. So B is not a component in G-D, and that's a contradiction. Yeah.
Sorry, could you explain the last part at the beginning, like where it comes from, about the edge?
This one?
Yeah.
Right. So I know that the boundary of B is big, but I can delete only half, like this. Let's say this number is 10. I can delete only like at most 5 edges.
So there's something that
cross the
can't
boundary.
be deleted, right?
Yeah. There's something that can be, but that we didn't delete and cross B. Yeah. Okay. Hopefully it's clear. Okay. So now let's talk about update time. I claim that it's gonna be like something like d over phi. And let's prove something without data structure first. The claim is that the total volume that we ever explore is going to be small, something like d over phi. Why? Because we only like continue exploring from active guy. Each of the active region, you know that the volume that you explore is kind of bounded by, like you can charge it, like the volume of the region is small compared to the number of deletion. So the point is, the region that you explore, you kind of charge to deletion by what? Like by 2 over 5 factor. So the total number of deletion is at most 2D, like summing over all U. So it means that, yeah, the total, if you sum over degree of U that you explore, it's going to be at most 2D over phi. No, 4. 2 times this thing. 4D over phi. Yeah. So we just continue, like once, yeah, continue exploring only when there are, you can charge your cost to the deletion, because you only explore it from active region. Okay. Any question about this? Okay. And next is that to implement this algorithm, right? What you really need to do is like you have a bunch of region, and then you're gonna merge a set. So that needs some data structure so that you can say that you have 2 sets, you merge it. And then you can, and you need some data structure that you have a set, you can list edges, like list edges incident to it, find the neighbor. So I will ignore that. Use some union find, use some basic data structure that's gonna spend like maybe log n factor. You can think about that. But to answer your question, basically the point is that we explore from active region. That's why like we just spend time proportion to D, not the whole graph.
Okay.
Yeah. Okay. So okay. Hopefully you are convinced that we can solve this problem on expander. Okay. Questions about this? Okay, let's do general graph. Okay, and here's the plan. We need some technology to do it. Okay, the first one it's called expanding balance separator, and then we're gonna build a hierarchy and then do the general graph. Let me start with the first one. Okay, it's a new object, so let's see what it is. Expanding balance separator looks like this. So it is the following. Let's say you have a graph, right? I claim that there exists a set of edge, call it F. This is F. Such that first is expanding. The set of this edge set is expanding. Note that this just means degree of F is expanding in G. Right? How expanding? Really good expansion, like 1/4 expanding. So that's the first property. And next is the balance separator. as the name suggests. Meaning that once you delete f from the graph, then the graph scatter. The graph split into small pieces. After you deleting f, each component here has size at most half. If you delete f, each component have size at most half. So expanding balance separator.
And just so I remember, so when we say edge set is expanding, that's like saying the degree of f is expanding.
Exactly.
Okay.
Yeah. Yeah. Degree of f is expanding in G. Okay. So let's see why this exists. Okay. And the proof is actually quite simple. The algorithm is like this. Let me initialize my f with everything, with all edges. Okay. And then I'm just going to check if f is expanding or not. If f is expanding, then we are done, because we can just return f. F is expanding, and G minus f. What is the size of the component in G minus f at this point? 1, because f contains all edges. Suppose f is expanding, then this is true, and this is true as well. We good? Okay. But if f is not expanding, then we need to do something. Okay. So if f is not expanding, then there exists a sparse cut with respect to f, meaning that you have this thing. There is a cut such that the boundary is smaller than 1/4 times 1/4 times this thing. Okay. So what we do, let me assume without loss of generality that S is on the smaller side. The number of nodes is less than half. If not, just swap it. Okay. And what we do is this. We're going to update F as follows. I'm just first adding boundary of S to F, and then remove all edges inside F from S. Removing all edges inside S from F. Yeah. Okay, so in picture it looks like this. In the beginning, F is everything, right? And let's say I find a sparse cut like this. Now I add edges here. These edges, the boundary was there before, so I didn't really add anything. And then I remove everything inside. That is strictly inside that I remove. Then check again if the new F is expanding. If not, let's say I find this cut that is sparse. Here, it means that this cut is sparse with respect to F inside here, right? Not just, I don't count this part anymore. The number of edges here is small compared to F inside here. Okay, so what I do, I just add edges on the boundary. This part was there before, but now here, this is the new part. Right? This is the thing that I add, and then I remove things from here. So this is F become like this. Everything put this part and these edges and these edges. And maybe I can continue. Maybe it looks like this. Is it clear, the algorithm? Okay. So let's prove that this algorithm works. Okay. So you have this one. So okay. So I claim this invariant. Like I want to prove this one first. Okay. The invariant is that each component in G minus F has at most half vertices. Half of the vertices. So in the beginning it's true. Because in the beginning each component has one node. Okay. But it's going to be true throughout. Why? Because when we find a cut S, right? Number of this is a new component. Every other component in G minus F looks like a singleton. But this is now a new component, but this have size at most half by our choice. When I find a new component here, this is at most half again. And look at this one. This one shrink. Right? It only shrinks. So you have every component only shrinks except the new one, which have size at most half. So you have this one. Good. So the second, like to be a balanced separator, you have it. And once we stop, we know that F is expanding. So all we need to, because that's how we define. So we just need to show why it stops. Any idea why it should stop? Why this algorithm should stop? So let's see the algorithm. Okay, let's see what happened in each iteration. Yeah.
If it's, oh wait, hold on. If it is 1/4 expanding, you won't be able to find a cut anymore, sparse cut.
Mm-hmm.
So you won't be able to keep cutting it up, right?
Yeah.
There won't exist a cut to do anything, right? Maybe.
Can you repeat that
I
again?
guess okay, so in every loop, we find the sparse cut, right?
Mm-hmm.
Once F hits that 1/4 expanding, there is no more sparse cut.
Yeah.
So we can't cut it up anymore.
Well,
I guess we can adjust the threshold, but.
so it could be the case that, like what you want to say is that if this thing becomes sparse cut, now it's not sparse anymore because we cannot remove it, remove something inside. But the thing is that at other point of time, I might find this thing and I add something in F here. So like there could be something that looks like a sparse cut here again because I add something back. Okay. So there is going to be maybe some other argument. Yeah.
It's something like each time we do an iteration of the while loop, we decrease the number of edges in F because like the number of edges in each of the components has to be at least like 1/4 of the size of the boundary.
That's the right idea.
Okay.
Yeah. So the claim is that whenever you make a new loop, you decrease the size of F. And that makes total sense. Why? Whenever I create a new cut, when I find a new cut, this cut is small compared to F from both sides. Like the cut that I find here, look at the cut, look at the boundary, this is small compared to f from both sides. Okay, so let's see. Okay, when I find a cut, right? Okay, I add something to f, which is the boundary of f, the boundary of the sparse cut. I add something, but how much do I remove? I'm gonna remove edges inside f, but the edges inside f is like, okay, it doesn't really matter, like you can check this, but the point is that the edge, like this is sparse with respect to f. So compared to the thing that you remove much more than compared to the boundary. Yeah. The boundary is small compared to edges, f edges inside. That's it. Yeah. So you remove more than you add. So you decrease the size of f, so it must stop. Okay. And you can calculate this, and it's like indeed more than what you add. Okay. By choosing, like, this is why I choose 1/4 sparse. If it's even 1/10, it's even better. But it might not be like 1 exactly, but yeah. Okay.
So do you have Slack there where you can get like better than a 1/4 expanding, like 1/3
I think
or something?
1/2 should work, but 1 might not work. Yeah. Okay. Okay, so we have it. Okay. And now we're gonna use this expanding balance separator to build some hierarchy. Okay. So let me tell you what do I mean by hierarchy first. Okay. So a hierarchy H of G, you think of it as a laminar family of induced subgraph. So meaning that it looks like this, laminar family. So it's like a set that contain each other, do not cross each other. Okay. So the root set is like the whole graph. The leaf set is just a singleton node, singleton vertex. And the non-leaf set, like this thing, maybe S, is basically the induced subgraph of some vertex set. You know what I mean by induced subgraph? It's just the graph containing all edges inside S. Okay. So that's the hierarchy. So think like it's just it looks like this. Any question about this? Yeah. Okay.
So, no, sorry.
Okay. And for each of this graph, I call it cluster. So like G induced by S is, I call it cluster. So it's like each cluster H is in the hierarchy H. Okay. And for each cluster, I'm gonna define two things. So yeah.
Also, for the non-leaf, is S some set of edges? So G of S would be the graph induced by that.
Oh, S is like a set of vertices. Sorry.
Oh, set of vertices.
Yeah. So think like the root is induced by the whole vertex set. The leaf is induced by some single node. And this is induced by some vertex set.
So non-leaf and cluster are the same thing, or?
Non-leaf, this is like a non-leaf cluster. This is a leaf cluster. This is a root cluster. Yeah. Okay. So a cluster, let's look at a cluster H. It has some children cluster H1, H2, H3. Okay. And there's going to be edges between children and edges that go out of the cluster. So the red thing, I call it separator of H, which is like edges between the children of H. It's like a separate H into children. Okay. So that's separator of H, denoted by sep H. And the boundary of H is just edges leaving H. Okay. So that's the two concepts that we will look at. Okay. So now, separator-expanding hierarchy is, I call a phi separator-expanding hierarchy, or phi SE, separator-expanding. It's a hierarchy of a graph. So it's a hierarchy, let's call it H. It's a hierarchy of G, such that for each cluster, the separator is expanding. Let's look at the picture. Okay. If I have a graph, the whole graph, then there's gonna be like, this graph gonna have some separator that separated into children. This separator is expanding in the whole graph. And now you get children H1, H2, H3. Each of these guys will have the separator. This separator of H1 is expanding in H1. Just inside H1. Right. And this guy is separated like each. And this is true for each child. Okay. Yeah.
When you say expanding, what would be the phi here?
Oh, phi, yeah. This is all phi. Good. Phi expanding. Okay. Question about this? It's like some concept. Okay.
So are we like trying to include like every possible subgraph here?
No.
Or like are we like fixing some collection?
It's like we fix some hierarchy, and like maybe like think of, let's say I have a grid like this. Maybe I draw it. Yeah. Like I have a grid, and maybe like my hierarchy looks like this. I just fixed some way to like hierarchical partitioning the graph. This is my children, and maybe like this is the children of this looks like this, and so on. Just fix some way to like, as long as you fix some way to partition the graph in the hierarchical way. And now, for each cluster, the separator is expanding, meaning that for this cluster, the separator here is expanding in this graph, and maybe the separator here is expanding in this graph. If you have this, then we call it like a SE, separator-expanding hierarchy. Okay? Now, just to kind of let you really understand the definition, let's look at it in another view. Okay? You can view this hierarchy in this way too. If I partition each set of a graph into parts, into like levels, okay? I have E0 up to EL. And I say that for each I, for each level I, EL is expanding in G minus, what is E more than I? This is like E I plus 1 union E I plus 2 union up to EL. Okay. So EI is phi expanding in G minus E more than I. Okay. If you look at this definition, then you can see that let's interpret what it means level by level. Okay. Yeah.
Would it mean that like if we have some EI that's expanding in a bigger part, it will also be expanding the smaller parts, or
let me explain that. Yeah. Let's try to interpret this level by level. Let's look at L, like the level I equals L, the last level. Like we have like level 0 up to L, right? For the last level, what do I mean? It means that EL is phi expanding in G because there's nothing beyond level L. So this is like the same thing as the red set like in the previous slide. So EL is like an separator of G. Now let's look at I equals L minus 1. Okay. Now this thing reads as EL minus 1 is expanding in G minus EL. But G minus EL has many parts, many components, right? It has this component, and this component. But what does it mean here? It just means that when you restrict yourself, when you restrict to this component, the EL minus 1 in this component is expanding in this component. Right. Recall that like when we say that something is expanding in something, it just means that for each connected component, the node weighting is expanding in the component. So you see that to say this thing, it's just really the same as say these three things at the same time. Make sense?
also each level is kind of, it's not the component, it's a collection of those components that we kept breaking. So like, for example, level L minus 1, would it be the three components that were originally broken into, or?
So this set EL minus 1, you should think of it as like the separator in this level.
Oh, into the smaller level.
Yeah. So EL, like each edge here is like a separator of that level. This just means like this is a separator, like this thing form a separator for every student of level L minus 1. And it's expanding in each component. Okay. Does it make sense? This is like a new concept, but yeah. Okay. We're gonna use it soon. Maybe not today. So, okay. So let's say that I'd say that like a level I cluster is a component in this level. So a graph G is like a level L cluster. And this thing, this is like level L minus 1 cluster. Okay. So that's the like terminology, right? And it makes sense, yeah. Okay. So I claim that a level 0 cluster must be a phi expander. Why is that?
It's just a point.
A level 0 cluster might not be a point. It's like level -1 cluster is a point. Because level -1 would be like G minus E more than this, which is, this is like everything. But level 0 cluster might not be a point. Yeah.
Would it be the case because like the level L cluster we know from originally is by expanding, and then so it's the connected components, meaning the level L minus 1 is also by expanding, and like if to take it all the way back.
Actually, not quite. Like level. So as you see, like level. I can only say this for actually only level at level 0. No other level. Like for other level, H might not be a phi expander, actually. Okay, and maybe try to convince yourself of this. Yeah, that is. So now that H only contains edges from level E0, because yeah, it's a component in. This is a component in G minus E more than 0. G more than 0. So H only contains edges in G0, in E0. And E0 is expanding in this thing. It just means that E of H is phi expanding in H, which means that H is a phi expander. Okay. Okay. So maybe just try to convince yourself of this. And next time, what I'm going to do is we're going to construct, or just as an exercise, you can convince yourself how to construct this hierarchy using the concept of expanding balance separator. We're going to see that on Thursday, but it's not hard at all. And once we construct this, we're going to see how to get the connectivity oracle for general graph. Okay, yeah, see you next time. Yeah.